This year we've got well over 350 people registered for this event, so we're scaling up. And very pleased to say that we will be holding the same event next year. It will be back here in Robinson, actual dates to be announced. And as with last year, for those who came, plenty of opportunity to give us feedback. We're going to be constantly tweaking this event, so if there's anything you don't like, any suggestions for how to improve it for next year, do please contact us or anyone on the committee. One of the bits of feedback we had from last year was that the delegates enjoyed all of the talks to academics, but they wanted to hear more from ARM about how we see the world. So we've put together this ambitious session with, well, you can see how many speakers we've got lined up for you. So this could go catastrophically wrong, but we're going to do our best to stick to time and try and give as much of a flavour of the research that interests us to you guys. The most important thing, though, is that you get to put a face to the names and the research areas, and you can then grab people afterwards and start talking to them. In order to try to keep things on schedule, though, we thought we'll do this, but we won't have questions here because we've got the much more important issue of drinks to get to. So we'll just stop, off to drinks, and you can grab whoever you want to talk to. For those drinks, they are actually going to be served in 2 locations because there's quite a few people here. One of the locations will be out over in the Wordsworth building. If you haven't been there, it's out that way where all the posters and demos are. We kind of expect most people will want to go over there to see the posters and demos. Also, if you've got a poster, please make sure you get over there quickly and put it up because some of the posters aren't up yet. But if it does get a bit crowded, there's a separate drinks location serving up on the balcony here. Hopefully, the sun will stay out and you can all go out and enjoy the grounds here. If it's raining, there's room indoors as well. And one slight correction just to say, I think it says dinner's 8 o'clock in the printed schedule. They're actually going to be serving from 7:30 to give everyone a chance to get through. So if you're hungry, dinner will be served from 7:30, but there will be plenty of opportunity to go whenever you like. So we are already 2 minutes behind our schedule. So I will now hand over to John Goodenough, who's going to get us back on track. Aren't you, John?
I will. Thanks, Chris, and good afternoon, everybody. So I'm the first speaker on here. My name is John Goodenough. Here's my face. So name, face. As Chris said, this session is really set up as an almost virtual speed dating matchmaking. So if you hear anyone say anything interesting, even if you think it sounds interesting, the next follow-up thing is to come and talk to us after in the bar, in the networking, over dinner, throughout the rest of the conference. In the event that you can't connect with the individual that you really want to follow up with or to figure out what's going on, your first points of call are then me and Chris, and I'll introduce why it's me in a moment. Where's the clicker? It's there. Okay. So I get the job of giving you a very high-level overview of ARM research. You'll be pleased to say, I'm pleased to say, I'm not going to talk about anything technical other than one thing. And I'm going to give you a few key messages. So I'm an old hand in ARM, and I was in the research group about 12 years ago. I've been off doing a few other things for the last 12 years, and I've come back. And I've come back specifically as one of the new activities that ARM is undertaking following the acquisition and by SoftBank and our subsequent restructuring. You can see one of the other new things up here is that we have a new logo. We're now lowercase ARM, not uppercase ARM. So there's been quite a few changes inside ARM over the last year, and if you talk to people inside the business, they will say that although our core mission remains absolutely the same, we want to be the technology, the architecture of the digital world, and to make sure that everyone is using our technologies and ARM technology wherever electronics is done. There's been quite a lot of soul-searching and focusing about how we go about doing that and how we go about achieving that mission. One of the things we're doing in ARM research is we're making investments so that we can better collaborate with you guys who are doing research out in academia or out in other pre-competitive areas to advance a collective research agenda. So this is really the only one slide you need to pay any attention to from me. So this is what ARM research does. We partner, and we're partnering specifically with you guys to accelerate a research agenda and transfer that knowledge into the ARM ecosystem. And you'll notice I say that ARM ecosystem, not just into ARM. This is about developing things that are not just going to see the light of day in ARM product and deployed into the world, but also about seeing technologies that may end up in our partners or may end up in an open source ecosystem. All routes are valid to create the solutions that folk need tomorrow. So what do we do in there? We're looking to the future. We're looking at what's out there in the technology landscape. What sort of things are coming down the pipeline? What's happening with semiconductor physics? What new ways can we build systems? I've just noticed James, who leads one of our groups, coming in, who's doing some research on things like plastic electronics. How are we going to build systems tomorrow? Are we going to do them on superconductors? Are we going to do them on plastics? Are we going to carry on doing them on silicon? So we need in ARM to work with you guys in collaboration to figure out where that landscape is going. We can't do it ourselves. We don't know everything. We need to build on ARM's partnership genes and our collaboration genes to work with you to collectively figure out both what's coming in terms of technology and what our research agenda is going to be to do that. And in order to do that, one thing that we've observed is, as we've been looking at how we engage and collaborate, that we can do a better job of that. Chris talked about how we entered a dialogue about what happened at last year's research summit, and we've based this year's on some of that learning. One of the things that I've come into the group to do is to listen to you guys and listen about how we do collaboration and how we undertake collaborative programs, and to make sure that we're doing that in a more effective and a more efficient way that benefits not just us, but also benefits you guys. And that's my job, right? My job is to make the collaboration between ARM and the world of pre-competitive research, whether that's done in academic institutions, in other pre-competitive industrial labs, or in strategic government laboratories around the globe, to make that more effective. So any ideas, any suggestions you have for me or about how we do that, please come and find me in the bar later, talk to me. Okay, I want to talk a little bit about our partnerships with universities. And we talked a lot there about collaboration. So our collaboration is underpinned not only by all of our researchers engaging with you on individual work streams and packages, but by what we do in terms of enabling you, providing you with access to IP, providing you access to tools, and providing you with access to other technologies. We've made some improvements this year to how we do that, and we'll hear about one specific thing we've done with IP access in a little bit more detail in a minute. We also help educate the next generation of students to use technologies to build tomorrow's systems based on ARM's technologies. And we'll have a session from our university program and a new and exciting area in education media to talk specifically about how we're making that collaboration to partner with you not only on a research agenda, but also on a teaching agenda later. One specific thing that I want to sort of make sure that you walk away with a message on, and this is really an appeal from me to you to come and tell us what you want from us, because we don't really know everything that you need to do your jobs effectively and efficiently, whether it's doing your own research or whether it's doing research in collaboration with us. What help do you need from us? What tools, technology, IP, access to funding from the European Commission, the DoD, in the States, or in China from the Ministry of Science? What help do you need to unlock that and to accelerate that agenda? We want to hear how we can enable you. We're going to start to roll out over the next 12 months quite an exciting program of what we're calling research enablement kits. Or today, there's a couple of things we call research starter kits. These will evolve and elaborate into things that we want to make sure that when you start doing research, whether your own research or whether in collaboration, you're not spending 1 month, 2 months, 6 months, 1 year trying to integrate our technologies together or technologies from our partners and its ecosystem, but you can get on with doing your research and advancing your field straight away. So research enablement kits are a really big thing for us coming up. The other thing that I wanted to talk about a little bit is what makes a good partnership with ARM. If your logo is not on here, don't worry about that. We're going to be doing an exercise of looking around, making sure that we understand exactly who we're working with, on what and why. But this logo speaks to the fact that we're a global organization. It speaks to the fact that we collaborate in many ways. We collaborate with individual institutions on individual programs. We collaborate with university consortia through organs like the SRC. My message here is there's no one right or wrong way to do this. We need to work with you, and we want to have a conversation and dialogue with you about the most appropriate way to work for you to advance that research agenda. So again, please come and talk to us about that. Slide here shows that we work very closely with the funding bodies. Here are 2 slides, one looking at our European projects that we've had funded over the last few years, and another one looking at the projects that we've got funded in collaboration with the US government funding sources. We see partnership with the public funding sources that are investing in education as a key way to advance research agendas, and we want to again work with you guys to understand how you're strategically approaching these funding sources. What areas are you working on? Where are you going after strategic funding? How can we help unlock the bids that you're going for, whether it's from the Commission, from a local European government, or within the US, or even the expanding this out into Asia. So we have a lot of experience of doing this. We can also bring ARM's partnership network to bear on that problem. So another good message there. Another area we wish to collaborate with you on. So, a couple of things just to come back to there. So one, new logo again. ARM's changed. We're open to have a deeper and broader engagement with you. We want to enable you to be successful, both in collaboration with us doing research with folk in ARM research, but also in collaboration with us doing your own research or supporting your teaching programs. All of those speak to how we want to have invested in advancing in extending our capabilities and want to collaborate more broadly. Second thing, it's all about feedback. You're going to see both me and a whole load of other people stand up, look at our faces, try and remember our names, come and talk to us after. If you don't give us feedback and you don't tell us what you want, we won't know what to do. So it's all about setting that dialogue up. And that's where we're going to put a whole set of faces in front of you now so that you can see them, you can clock them, and you can follow up with them. And the last thing, if you can't remember who to follow up with, it's me. Or it's Chris as the first port of call. We'll point you and route you to the right place. Okay, that's enough from me. I have overrun. It was predictable. I'm really pleased now to introduce you to one of the areas which we've been working on in terms of this whole area of enablement, and particularly research enablement, but also enablement that's going to help support teaching agendas as well. And that's about making us easier to deal with and access to our IP easier and smoother. So I'm pleased to introduce Phil Burr from our IP group, who's going to talk to you about a new program we've got to enhance and open access to our IP. Phil.
Thanks, John. Yeah, hi. So I'm Phil Burr. I'm in ARM CPU product marketing group. So I'm responsible for a whole bunch of CPUs. But as part of that, I'm responsible for a program on the CPU side called Design Start. So Design Start is about making access to ARM IP as easy and as simple as possible. And this program actually has been running for quite some time. So we started before 2010, where we made access to thousands of physical IP libraries available. And we provided a fixed configuration ARM Cortex M3. And so that was available for actually both commercial and research and academic use. We made Cortex M3 available for teaching a little bit later, and then we created a design education kit around Cortex M3, and Khaled, a colleague, will talk a little bit more about that later, so I won't cover that. What we did a couple of months ago this year was we added Cortex M3 into that, and we also made access even simpler, so that both for commercial and evaluation use. And then today, actually, I'm pleased to announce that we have made access for research even easier. So that means that if you're doing academic research, you can access Cortex M3 and Cortex M3 and their subsystems, that IP, on a click through. So you turn up to the website, you provide a bit of information, we just check that you're actually from a university, and then you can download it on a click through. So it doesn't need to go through your legal department, possibly. And again, Khaled will talk a little bit more about it, but we will have a Cortex M3 based design enablement kit available in a couple of weeks. And then we provide access to the physical IP libraries on a click-through, the front-end views, which is the views that most people use. But some people go a little bit further and want the back-end views when they're going towards implementation. And some of those views are, we work with foundries with those, and so we're hoping to make those available on a click-through later this year as well. Some of that is outside of our hands. So what is Design Start and what does it enable? Well, we believe it's the fastest route to research with CPU and physical IP. So it's this simple, no risk access. You can download and get researching almost straight away. We provide access to two very proven CPUs, Cortex M3, Cortex M3, and lots of physical IP libraries that have been used in many, many, many different designs. So the idea is that actually you don't need to worry about these systems working. They're proven, they're out there. But it's not just the IP. It's, okay, you've got access to a CPU, the subsystem, or the physical libraries. What do you do with them? Well, you need tools, you need know-how, and ARM has, the ARM ecosystem has hundreds of different tools that work on ARM CPUs. There's an incredible choice, some of it open source and free, some of it commercial and paid for. It's the choice and that wide knowledge base that really makes a difference. So it accelerates your research and allows you to concentrate on the bit that you should be doing rather than getting this base IP up and running. So we have three strands from a CPU point of view, three strands to Design Start. So we have Design Start Eval, which is about evaluation and teaching. And for research, we have something called Design Start Pro Academic. And if you're moving towards commercialization, we have an offering called Design Start Pro. So Design Start Eval is instant access. It's open to anybody. There's no signature. You just click, download, and off you go. That's the full subsystem RTL. The CPU RTL is a fixed configuration. It's synthesizable, but because it's open to everybody, we just have to be we make that non-configurable. For Design Start Pro Academic, then this is for research. You tell us a bit about yourself. on a web form. You can once we've just checked that who you are, you can then download with the EULA, as said, and you can manufacture up to 1,000 units with that IP. So it's perfect for research, test chips, that sort of thing. And that's the full subsystem and RTL. And then if you want to commercialize, then you can access the same IP, slightly different agreement, and you can access without any upfront fee. So for commercial deployment, then actually you can start, and companies do start developing their chips based on that, without paying ARM any money at all. So Cortex M0 and Cortex M3 enable a very broad set of products. So Cortex M0 is a very small processor. It's used in tiny energy sipping applications. It could be smartwatches to smart pills. Cortex M3 is a more mainstream Cortex M processor. It's used in many embedded devices, and it could be things like smart thermostats, smart lighting, and so on. And I mentioned that these devices are proven. So this is, it looks a bit like a marketing slide. It is, but the point of this is, we've shipped. The ARM partners have shipped 20 billion devices based where Cortex M0 or Cortex M3 is the main CPU on that device. So that does mean that you can crack on and do your own research and without having to get that base IP up and running. And I think that so today, I think today that works out to be. So last year we shipped, for every hour we shipped, or partners shipped 500,000 devices there where Cortex M0, Cortex M3 were the main device. It's not just the CPU, so we provide a subsystem around that CPU. So with Cortex M3 we provide a fully verified CPU. You can configure that and you concentrate on adding your own IP or your own peripherals around that. For Cortex M0, we provide an example subsystem. Again, you can concentrate on adding your own things. And if you want to modify them, you can. We provide some, other IP to go with them. We don't provide a whole range of peripheral IP. That ARM doesn't have that, but there's lots of peripheral IP out there in the ecosystem. With Cortex M3, in fact, for both devices, Cortex M0, Cortex M3, for design start eval, we provide that ready to run on an FPGA board that you can get from ARM, or you can take that and run it on your own FPGA. And we also have ARM Embed, which is an IoT platform software, so it provides things like security, device management, and the idea there is that if somebody's writing some IoT software on that device, they can concentrate on the application part without having to rewrite all of that underlying software. They can get that free, and that's majority of that is open source. So let's look at a couple of case studies using, in fact, Cortex M0. So one case study is from Utar, which has created a four-core Cortex M0 based device, and the main purpose of that research was to investigate adaptive network on chip architectures. And I think as a result of some of the work they did, they've created a reusable multiprocessor verification platform, and in fact they've created a very capable IoT device and learnt an awful lot in that process. And so they found it very useful to do that work, not only from the NOC research, but also actually creating a device. And then another example is from UC San Diego, where they used Cortex M0 to do some 3D IC partitioning optimization. As you can see from that slide, then using they happened to use the Cortex M0 for that, and through their algorithm they demonstrated a 16% performance improvement compared to the current state of art. So again, they were very delighted with the use of that IP. So let's take a quick look at the physical IP. So for research, we provide standard cells, memory compilers, and GPIO, and it's across a whole range of different foundries. So this rather eye-watering table it kind of shows you the breadth of physical IP libraries that we have. And it is stretching from 7 nanometers on the left all the way to 50 nanometers on the right, so a pretty broad spectrum. And you can access the majority of that very quickly through Design Start. Some of the more recent, the more advanced nodes, then come and talk to us about those. But the idea is to enable you to do your research with that physical IP. And just looking at some of the physical IP that we provided to universities last year, then there were a total of 111 access to IP provided. And as you can see from the pie chart, actually a lot of that is fairly advanced nodes. And actually it surprised me. I thought a lot of it would be much more spread across the nodes, but actually some fairly advanced stuff there. So we are, it's about enabling you to do that research. So how do you get started? Well, the 3 programs I talked about, so Design Start Eval, you just go, you go to designstart.arm.com or just Google Design Start and you should get to it. You register, you click and download, and it's downloaded in minutes. For Design Start Pro Academic and the front-end physical IP libraries, then you register. It tells a little bit about your project. We just check who you are. We approve, and then you click and download. And in general, that takes less than a week. And then if you want to access other ARM IP, then actually we do provide other ARM IP, so not just Cortex M0, Cortex M3. We provide other CPUs as well. And then in that case, then register or talk to some of the guys you're going to see today. But register, tell us a bit about your project. We'll have a discussion about it. Hopefully we can approve it. And again, you can download. Okay. Thank you.
Right, thanks a lot, Phil. So just stand there, stay there, Phil, stay there. This is Phil. You want to talk about Design Start or IP? Talk to Phil. Okay, and just one comment on that. So I'd say this has been work that's been going on for the last 6 months, again, to improve how we're engaging, improve how we're supporting and enabling you guys. Look to see over the next 6 months, a year, more things coming down this channel. You'll notice that we didn't really talk a lot about tools there, for example. And we're aware that we need to kind of get a more coherent sort of offering and bundle together in that space. So lots more coming in that sort of enablement space. Now, one area when we enable people, we don't just enable people to do research, we're also enabling people to do teaching. And one of the things that we've been doing for quite a long time now is specifically looking at how do we enable people to do teaching in and around ARM. And I'm very pleased to invite Khaled Benkrid up onto the stage. Again, you see his face at the start, you'll see it at the end. Khaled runs our university program, which is oriented to providing all of the stuff we do towards teaching. And he's also got a really exciting new program to talk about as well on education media.
Thanks, John. So, Khaled Benkrid, Director of Education and Research at ARM. I look after the education brief, and our vision is to play a leading role in plugging the education gap. This is something that is very high on the political agenda, as many of you know, which is the mismatch between what universities are teaching and what the kind of skills and competencies that industry want. And we do that by basically helping academics and students harness state-of-the-art technologies from the ARM ecosystem. Now, a lot of what we do is actually on behalf of the partnership of the ARM ecosystem. So our university program in many ways is a meta-university program because we work with other licensees university programs. So through us, you work with NXP university program, with Xilinx university program, with many of our partners university program. By enabling them, we enable the whole of the ecosystem. So I said, why are we doing that? We're doing that because this gap, there are a lot of studies that show that this gap is growing in computer engineering. There are many reasons for that, but one of the reasons is the pace of technological changes. Technology is changing at a very fast pace and often outstrips the academic or the educator ability to keep up with this pace, especially with the added pressures of balancing research with teaching. And I know that I've spent 13 years in UK academia, so I know all of the pressures that are on academics to balance research with teaching. But failure to address this gap has serious socioeconomic consequences, and there have been a lot of studies that estimated the cost to the economy of doing that. Now, we think that as the company which sits at the center of the largest ecosystem in computer industry, that we ought to play a leading role in addressing this gap. How do we do that? Now, we believe that industry should play a role in content creation and not just as a technology provider. So I've dealt with industry from the other side, where you get hardware and you get software and then you're on your own, basically. So what we do is that we create content to go with the hardware and the software. We believe that technology is also very important as a key to addressing the education gap through interactive and content-rich, media-rich content, through online delivery and collaborative services. We're dealing with students nowadays that are Web 2.0 generation. The attention span is very short, and they are really used to interactive content. They grew up with the iPad and the instant reaction. So we need to move with the times and provide media-rich content. And we do believe also that we have to exploit technology for automated assessment. We think that machine learning and artificial intelligence are ways to scale up the education process. Now, the ultimate goal, the philosophical question here is, could we accelerate the process of creating content to meet the dynamic needs of the industry? So there's something that we call the accelerated learning here that we're trying to achieve. Now, there are two groups within ARM Education. There is ARM University Program, which provides education kits in the form of lecture slides, lab manuals, code, software licenses, and hardware. This is free of charge to university professors worldwide. And ARM Education Media, which provides self-taught and self-paced online education kits in the form of online courses and e-textbooks. And these are available on a subscription model to everyone, so not just educators, but also students and also any kind of engineers out there. They're multimedia rich and they're highly interactive. So I would like to say a few things about the ARM University program. So our flagship offer to academia is what we call the education kit. This is a self-contained package that contains everything that a professor needs to teach confidently with ARM technologies. And by that I mean teaching materials, lecture notes, lab manuals, demonstration code and projects, professional software, that's very important, hardware from our partners, and also we invest a lot in training the trainers. So we have a lot of train-the-trainer workshops where we train the educator on our content, and we understand also how do they want to tailor their content to their particular needs. And all of this is free to qualified academia worldwide. Now, how do we come up with our content roadmap? As John said, it's a two-way street. Some of it is what we call the push-pull. Some of it is thought leadership. It's ARM looking 5 years down the line or 10 years down the line and saying this particular topic or these particular topics are very important, and we ought to start training our students on these topics from now, so that in 5-10 years' time, when the demand in industry becomes strong, that students or graduates will be ready. That's what you call the push. The pull is demand-driven. So we meet professors from all over the world at a variety of conferences, and we do listen to the needs of academics, and that influences our roadmap of content creators, of content creation. Now, this is our current roadmap of education kits creation. We started in 2013. As you can see to the left, we created a couple of courses on embedded system design, one on efficient embedded system that goes into the details of how an embedded system is designed, and another one which takes a high-level approach using Embed MPI, which is all about productivity. Then following year, we created an education kit on DSP, and two on SOC design. So as Phil said, we created one on Design Start M0. So we teach students how to build a simple SoC based on Cortex M0 and synthesize it on FPGA, and then program it using a normal software toolchain. In fact, we use the Kyle MDK tool to program it in C. And we had another course on advanced SOC design, which is based on platform FPGAs, on the Zinc FPGA from Xilinx. The following year, we created a couple of courses on Internet of Things and real-time operating systems. And then last year, we did one on mobile gaming, so exploiting GPUs. Again, this is something that industry is telling us. Gaming now is mobile first. So people now develop games on mobile phones and mobile platforms, whereas 10 years ago it was all PC-based. Now, programming for mobile is not the same as programming for PCs, as you know, and there were some interesting talks this morning about programming for low power as opposed to programming for performance. And then this year we launched a couple of education kits, one on Linux kernel development and another one on robotics and mechatronics. By the end of this year, we'll have one on computer architecture, and the last in this series is on VLSI design. So we're going to use Design Start M0 and take students through a process of a SoC a development process from specification to fabrication, so GDS2 all the way to foundry. Now, there are consistent pedagogical basically approach here. There's our guiding principles and design of all of our education kits. It's hands-on, competency-based, so it's all about learning by doing, but it also covers the theory and the practice. So it's about deep learning, cover the theory and link it to the practice. We insist on low cost of access and ownership, so we invest a lot on sometimes even design and hardware platforms so that the cost of ownership to the student is less than that of a textbook. So most of our hardware platforms for teaching are sub $50. And the good thing is that you can use the same platform for multiple courses. In fact, one platform could use for 5 courses. Now think about the economies of scope that you can gain out of that. You can equip your lab with one hardware platform and then use it for multiple courses, hence saving yourself time about hardware obsolescence and software installation and all of that. And we do take care of that. So most of our courses are available on multiple platforms from different partners, and we work with our partners in order to achieve that. The idea here is very simple, concentrate on pedagogy, that's what you're very good at. Let us worry about all of these nasty details about hardware obsolescence and software, etc. And we build in a maintenance and update cycle in all of our courses to make sure that our courses actually ride the wave of technological changes. So every 4 years we have an update of our courses so that we adopt the latest technologies from the ARM ecosystem. So to give you an example, our efficient embedded system course that we launched in 2013 was based on V6M architecture, but now we're working on V8M architecture, so it exploits new features of the latest architecture from ARM. Now, there is a workshop, there are a couple of workshops running at this just to give you a flavor of what we do. We ran one session, one edition of it this morning, and there will be a repeat of it tomorrow afternoon on VLSI design flow around Cortex M0 with Dr. Matthew Swaby from Purdue University. Now, we have really been very successful with the ARM University program. We received a lot of requests. Our courseware is actually deployed in over 1,000 universities worldwide. But we received a lot of requests from academics and non-academics for content that could be consumed directly by students. So we created ARM Education Media as a digital-first publishing operation that produces online courses and textbooks in print and online formats. This is really to complement what ARM University program does. And the roadmap is very similar, as you can see. So for each of the education kits that I mentioned, there is an online course equivalent. And this is, we replace the kind of lecture slides with videos that and multiple choice questions that students could consume directly. So think about the flip classroom model, whereby you can give these videos to your students to consume at their own leisure, and then you replace the lecture with tutorials and labs, hence, saving your time, saving students' time as well. And the early feedback that we got, so we launched this at the end of 2016, was that it's really increased the student satisfaction level. So we have 5 courses available at the moment, as you can see in the blue on the left, and there is a roadmap for completing the 12 core courses that I talked about earlier. Just to give you a flavor quickly, this is one of the courses that we created on IoT. As you can see, there are a number of modules. Each module will consist of this lecture slides with notes, as you can see. So this IoT course teaches students how to build a simple IoT system using mobile phones as hubs. So how to build an Android app, and then how to link it to a thing with Bluetooth LE, and then how to connect it to a service on the cloud. As you can see, there are labs here lab manuals with videos that show the complete process, culminating in the creation of a full IoT demonstration. I think one of these is there is a health application, and there is this weather station, as you can see, monitoring the temperature and humidity, etc., remotely using your phone as a pilot. And just to finish, there is textbook as well program that goes with it. Again, this is as a result of demand that we got, especially from North American academia. There's a textbook culture in the US. So we created also a textbook publishing operation. I'm pleased to say that our first textbook was published a couple of months ago by Dr. Alex, the author was Dr. Alex Dean. So this is available now in print and online formats. And we are actually interested in working with you guys. We're commissioning authors for the roadmap that I showed you, but also other textbooks as well. So please talk to us if you're interested in collaborating with us on content creation and any of these topics. Thank you.
Thank you, Khaled. Khaled. So, remember, you want to talk about the ARM University program or ARM Education Media? Talk to Khaled. So, obviously, the training, as Khaled said, the training in the next generation is really important, because if we don't train the students, then we won't have anybody coming into our research labs to actually work on all of the interesting research problems on our research agenda. And that's really why we're kind of pushing that sort of education thing. What we want to flip to now is to actually talk about what is ARM's research agenda? What would we like to collaborate with you on to accelerate? So I'm really pleased to invite up Stuart Biles. Stuart's one of our ARM fellows, and he's going to talk about our research agenda.
Thank you, John. Okay, so for research agenda, I guess a bit of background would be a little bit about the ARM research group. So we're set aside from the corporate groups within the company, and one of the things we do is liberate money from them, and they're often not so happy about that. But the intent from taking some of their revenues is to invest that in some further term research that will either benefit them directly, so we hope to get some research findings, some intellectual property heading back to the product groups. It might be that we come up with an idea that doesn't really fit inside an existing product group, and we come up with a business plan for a complete new product group to be set up. Or it might be we spend some of that money to help the broader ARM ecosystem come up with materials that are useful, say, for the academic community. So one of the questions we get asked by the product-facing guys a lot is, what did research ever do for us? Hopefully we've got a good track record with many of them in terms of things that we've come up with. We also get asked quite often, what are you going to do next and why? And it's probably that why bit that I want to talk about now. So, you know, we have a bunch of bright people in the group, and we have many ideas. Can't research all of them. So what we try and do periodically is to come up with a strategy which tries to encompass, if not all, at least the majority of the activities within the research group at large. And the story this year is really the convergence, the collision of two scaling trends. One of those you're fully aware of is that transistors, they're not scaling as well as they used to. In fact, they're not getting much smaller at all, not getting quicker, and they're getting more expensive to make use of. So, guy behind a lot of this work originally in research to kind of track the trends. Greg, he's away. I think you could probably get hold of either a Rob or a Brian if they're in the audience, if you want to talk about our predictions for where transistor scaling is going to go to. But the upshot is that we can see is probably from like the 5 nanometer node. That's probably the endpoint for kind of commercial scaling of silicon transport inside the transistor. Things are going to get more expensive. If you can find a way to either get the volumes, so you're going to be a very high volume seller, or you're in a domain where people are desperate for solutions and they're going to pay extra revenue to you, then you might be able to stay on the bleeding edge process. Otherwise, you may stop, kind of get off the escalator there. So that's probably the one scaling trend that we're concerned about. The other one is the IoT, and lots of people have got extrapolations about how many devices there's going to be. We can probably agree there's going to be a lot. But if you add on top of that, they're all connected, actually the bandwidths involved are pretty astounding. So probably the convergence of these two scaling trends is, how are we going to create computer devices that are going to generate the data, communicate the data, and process it all. Now looking at the stock slide, I probably actually say connected drones, live streaming, may be solved already without technology. So I've just come back from holiday, and pretty much every beautiful place you went to had a placard on it saying no drones allowed. The most amusing one was I was by the seaside in Maine, saw a guy park his car, get a drone out, flew it out across the bay past a nice house, which belonged to Mr. Bush Jr., was one of his retirement homes. It took 15 seconds for two suited people with sunglasses to come out and across this person. So it might be live streaming drones, not a problem. No technology needed. Okay, so for the kind of research group strategic agenda this year, this kind of indicates areas where internally the researchers that we have are active on. If you're looking for traction, this is a good bet of topics to come and talk to us with. After me, you're going to hear from the technology thrust leads within the group, and probably a fun question over drinks is to get them to explain how their current activities align with this or not. It's not meant to be all-encompassing, so that we'll never get a complete logical explanation for everything we do. There are plenty of opportunistic things we get involved with. But probably the first one is, given the benefits of transistors are petering out, is it time to rethink about how we spend transistors on the system? So, I come from a CPU background, CPU implementation and architecture. For decades, the right answer has been, don't do anything too dramatic, just make your instruction window deeper, consider more instructions, issue more. You didn't need to impact this software to do that, and that was the right answer for so long. And I know from the interesting work I've read over the years, there have been many counter proposals to that which incurred potential upsides, but also required some perturbation to the software stack. And at the time, the right answer was probably to put those to one side, tread the traditional path. I think it's now an interesting question as to whether, we know we can't continue to scale processes in the ways of the past. The software stacks have changed a lot over the past 1-2 decades as well. So I'm quite interested there of, is it time to look at new techniques which mix up the software-hardware boundary and come up with potentially benefits without the kind of commensurate increase in transistor budget needed. Other area, if you look at scale connected compute intelligently, is there's going to be a plethora of devices all shouting towards the cloud. Sending all of that data back there and processing it within the cloud is probably not going to work for a number of reasons, performance and bandwidth being one of them. So we're very interested in models where you can distribute the processing across the network, determine where the right place to hold the data is, where the right place to do the processing is. In concert with that is, what is the software model that's going to allow that in a friction-free manner? Nobody's going to be wanting to spend their time targeting different architectures and different systems, different software stacks to try and distribute this processing task. So low friction to the programmer approaches to this are going to be an essential aspect. An example of that would be to proliferate access to ML across the network. So initially, ML was very much focused with train and infer in the cloud. We very much believe that there are good reasons that you want to push that processing towards the edge, be it kind of performance or bandwidth, certainly privacy and availability of service. There are many, many reasons why we feel that the smaller end of the processing spectrum needs the ability to pick up these machine learning, certainly inference tasks. Final one is, been through a few iterations in how we expressed it. I think, to me, remove untrustworthiness or otherwise increase security, increase trust in the compute systems that we make use of. Again, the observation there is the Internet of Things is going to be built of many diverse systems from many different designers. And if you look at the problems that they have, many are focused on really the product design issues. They're focused on getting something which demonstrates the behavior that the consumer wants and getting it out there. Security is a really tough problem, and many people really aren't investing in the bedrock that is needed. So in ARM research, we're very interested in, what can we do tangibly, which is going to lift the bar for everyone. It may be that we come up with architectural support that helps it. It may be that we find software paradigms that can embrace it too. Is that Amber for my 5 minutes or 1 minute? Okay. I know, I was so harsh running other people. Okay, so that's pretty much the strategic agenda. What we're going to do next is to get the leaders from each of the research thrusts within the group to give a bit of an overview. First one would have been Matt, but I'm going to stand in for him. So Matt is an example of the kind of researcher that we want. So he didn't want to do this pitch so much that a complete 9 months ago, he embarked on some activity which ensured he was on leave today. So if you have any students out there who have that kind of foresight, I would like to hear from them. So anyhow, I'll talk to you a bit about architecture. So that's been, ARM's bread and butter, very profitable aspect for ARM business-wise for a long time. And ARM research have had a great history of researching new areas and delivering content into both the architecture group and into the CPU design group within ARM. So the architecture is the interface between the software domain and the hardware domain. And there's just a flavor of areas that we're interested here. Moving between, reliability, we're seeing increasingly our processors used in areas where, the downsides, if things go wrong with, it's not that one. Is that 10 minutes total for me?
So you keep going.
I keep going, okay. I've got a new 5 minutes.
You've got a couple more minutes.
Excellent. Okay, so we're seeing, ARM processors are used in cars, they're used in drones, they're used in planes. Increasingly, the kind of physical fallback mechanism that existed, so things like ABS brakes and whatnot, are disappearing. So as you head more towards autonomous cars and drive-by-wire, just taking automotive as an example, it's increasingly important that you can trust that the compute device works all the time. So reliability without necessarily having to revert to the things that NASA looked at, triple core redundancy is of interest to our customers and to research as a result of that. Acceleration, so we spend a lot of time in the architecture team in research, understanding new applications, understanding how we might accelerate them inside the processor. So there's an aspect of understand important new workloads, machine learning being one of them, and figuring out how we can optimize the execution of workloads on general purpose machinery. Aside from that, there's also interest in how do we interface with domain-specific accelerators, how do we synchronize and communicate with them effectively. As I said, on the kind of strategy sides, we think IoT is going to be huge. The M-profile core from ARM is well set up there to be an important aspect of that. It's a smaller architecture, but it's also being used in platforms which are connected, open to attack from the internet. So the ability there to kind of increase the performance potential of these devices, yet end up with good, robust software stacks running on them is of keen interest to us. Scalability in next generation systems, I think, talk again to, I spoke on how do we get more without Moore's law? How do we scale performance without scaling processor size? So there's interest there in, what are the techniques we can deploy in general purpose cores to get better capabilities, to allow people to embrace more complexity in their software stacks. Also paying good attention to how the software stacks migrated over time. So hopefully before some of you retire, C may not be the prevalent source code for people, and different runtimes will be there. And if they are, we should be able to make use of them and exploit them. I think that's me speaking from that. Next guy coming up is Erik van Hensbergen. This is me, and that is him. Face the front. Thank you, sir. Okay. So Eric leads our large-scale softwares and systems group.
Large-scale software. Software and large-scale systems group. Let's flip back. So I lead the software and large-scale systems group. That group's split between Austin and here in Cambridge. We work on a number of different areas, and I have more detailed slides that you can look at while I talk. So my group was the leading front for our high-performance computing developments. I gave a keynote last year here at the summit on some of the details of those activities. And we've got a number of collaborators in the US. The Sandia guys are here, in fact, a lot of them that we collaborate with, as well as in Europe in the Mont Blanc program, and several of our collaborators are here as well, and also with our friends in Japan and Aitken, who I haven't seen yet, but I think are coming here. We've had a lot of success over the past 4 or 5 years from when we started getting involved with HPC and getting ARM bootstrapped and pointed in the right direction. We're starting to see system deployments now that are coming out with credible and competitive solutions. And so as a result, within ARM, we've got product groups that are now engaging and helping with the software and tools to support high-performance computing. We've had the architecture product teams release the scalable vector extensions. And we are sort of now shifting towards looking at helping our partners that are producing silicon and systems be successful in those deployments through code optimizations, as well as continuing to evolve the technology. And so we're continue to be very interested in collaborating with folks around high-performance computing applications, workloads, runtimes, operating systems, microarchitectural designs, accelerators, all different manner of functions in that, and we're really interested in continuing that engagement. In a sort of related field, we've been doing a lot more recently in high-performance data analytics. Within my team, we've brought on some new folks that are more senior and involved in high-performance interconnects, involved with open source communities like OpenSHMEM, and really looking at sort of the transport side of the equation, mostly from a software perspective. We're not getting into high-performance networking hardware or anything like that, but we want to make sure that hardware works really well with the ARM hardware and with our software stacks. And we're also spending a lot. We had done some work before in analytics and graph analytics, but we're looking at it now with new intensity. As we've grown the group, we've brought on people that specialize in that area, and we're going to be doing a lot more focus in that area. And more of the data center and server side, we've been looking more at serverless sort of software stacks and how we might better design hardware for those. And that's playing into some of that IoT strategy and dealing with data problem as we get to 1 trillion devices, producing all this data and flooding the network with it. How can we better design systems to consume that data, aggregate that data, and how do we make that easily programmable and do more of a first-class distributed systems approach, which is sort of more of a return home for me because I came from a distributed systems and operating systems background. It's a relatively new area for ARM research to be getting into, and we are looking for collaborators in that area. So that falls through a bunch of things in hardware software co-design, especially around network-oriented systems, event-oriented systems, operating systems, and distributed systems. And of course, because of the IoT focus and things like that, aspects of security are going to be very important in that world, as well as performance and efficiency and tail latency and so forth. So that's another area that we're looking for a ton of collaboration, and it's a new area for us, but we're rapidly ramping that team, and some of that's in my team, and some of that will be in some new skill groups that we're bringing up within ARM research. And that's me done, and I did it in like 5 minutes, not even 6, and this is my face.
Okay, so you've heard about architecture and HPC, which are two well-established application domains. Our next speaker, Chris Emmons, is going to talk about ones that are emerging and are not so well known yet. Chris, come stand up.
All right, hello everyone. So this is my one slide. Hopefully you can enjoy this throughout the 5 minutes that I'm talking here. So I'll spend the next few minutes kind of talking about how we track some of these emerging technologies, as Stuart said, that haven't found a home in one of our core research groups yet. So in a way, the Emerging Applications and Implementations group is kind of an inlet of new research areas where we kind of digest those for a while, work a lot with academics in the area, and curate those ideas before they spin off into the research groups. So some new technologies that directly align with some of the other research groups that you heard from already, they'll just start in those research groups. So we're kind of looking at newer stuff that hasn't really found a home yet. So the number and breadth of research areas that are important to ARM is quite massive, as you can imagine. So our vision as a company is to really be a part of compute wherever compute happens. And that's in a lot of spaces, in an increasing number of spaces. So as part of our research charter, what we do is identify and track. Right now we're tracking over 100 potentially disruptive and emerging technologies. So we look at things like the time horizon to impact, how that impact might disrupt the industry, disrupt the partnership, and we look for opportunities for us and for our partners in these spaces. So many of these technologies fall within areas where you all here in the audience and in academia are the experts. So we want to work with you in these spaces. So an example of that, I'll try to put a few examples in here throughout the talk of kind of the shape of collaborations that we do. So we've engaged with professors and students to collaborate on assessments of things like carbon nanotube FETs and spintronics, for example, and built some research papers around that to help digest the technology. So out of the more than 100 potentially disruptive technologies we track, a few of them we take and start research internally in the subject areas. So these are the broad areas here that we're looking at, and I'll go through some examples in each of those. So one area of interest is robotics compute. While robots have been around for dozens of years in an industrial setting, there's new advancements in sensor technologies and in machine intelligence that are helping robots find homes in new places. So one of the more obvious ones is transport, but also in healthcare, precision agriculture, and other places. So we're very curious to hear more from you about what kind of sensors you think will find their way into robots, and perhaps just as critical, the algorithms behind taking that sensor data and doing something sensible with it and understanding the context of the world around it. So if we're able to do that, and the analysts are correct, we're going to have a ton of free-range, autonomous, intelligent robots wandering around the world. So one of the key things that we're also very interested in looking at is how to make these robots safe. So any ideas on how to build safe robotics platforms, from architecture through things that we can give to academia and to researchers and industry to make sure that that happens, we're interested in looking at that. So compute isn't just happening behind metal and plastic the way we often think about it. And one interesting area is at the intersection of biology and compute is bioelectronic medicine. So bioelectronic medicine is where we have some external devices or perhaps implants that monitor and then stimulate the nervous system. And researchers in this area have made promising advances in treatments for conditions of inflammatory diseases like rheumatoid arthritis and Parkinson's. So there's some impressive work going on there. And again, another example of a partnership, we're partnering with the Center of Sensory Motor and Neural Engineering at the University of Washington to help support them in building a brain implantable system on chip. So that can be kind of a platform to help accelerate some research in these areas and help to treat neurodegenerative disease. So moving on, at the intersection of biology and data science, so technology improvements have really driven down the cost of generating data in the bioinformatics domain, specifically with advancements in DNA sequencing. So as costs continue to drop there, we can imagine a world where we don't just sequence our DNA and analyze our DNA to figure out some of our ancestral background, but we can actually perhaps analyze our DNA on a regular basis, identify mutations in our DNA that we know are precursors to like cancer and will cause cancer, and perhaps we can start treatment early and improve outcomes for patients. So that's some exciting work. The first work we started in that space was really kind of meat and potatoes for ARM and focusing on improving sequencing on ARM IP. So you can actually see a demo of that we've worked on in the demo section of the summit. So while we're helping others accelerate discovery in their domains, we have our own large data sets within our group in ARM's core business around architecture, microarchitecture, complex systems. These are very complex systems now that very few people, if any, understand completely. So if we can mine these large data sets, if we can apply some new data science techniques and new machine learning techniques, we're looking to improve our microarchitecture. So we have some internal work going on in that area. And finally, as we're delivering all these low-power sensors, perhaps always-on sensors into robotics, and we're improving our IP and reducing the power consumption, increasing the performance, these all trickle down into the consumer market and into mobile systems. So as they trickle down into mobile systems, new platforms emerge from watches to rings to one platform I'm pretty excited about is glasses. That's been on the radar the research radar for some time. But it seems possible now that we can actually really develop a compelling lightweight platform that then people will generate content for and hopefully bring some interesting content like augmented reality content to the masses. So in that respect, we're looking at technologies that support AR and working with some of you here, like at the University of Manchester, ICL, Edinburgh, and more, on techniques such as very low power SLAM. And there was a good talk earlier today in one of the sections on that. So I went through a wide variety of topics very quickly. Key message here, we're interested in a lot of different areas. There's a lot of different ways we can collaborate together. And find me, here's what I look like. Find me here at the conference, and I'm happy to talk about any more of these subjects. Thank you.
Thank you, Chris. So I chaired the last architecture and memory session just before the coffee break. All 4 talks there were about the interface to memory, and 3 of them were essentially about it doesn't matter how good your processor is, if the data's not there, you can't do any useful work. So our next speaker is from the Systems and Memory Group, and that would be Stephan Diestelhorst.
All right, good afternoon, everyone. Thanks for staying. I'm not quite the last person, but I try to make it quick anyways. This is a busy slide. Let me, guys, walk you through what I think the landscape for systems and memories really looks like. We look at applications first, and applications used to look quite simple. They had fairly regular structured data sets on the left. And with more processing power being available, more sophisticated data structures became available. So these days we actually have fairly different data layouts. We still have a lot of applications using structured data in various sizes, small data, big data, up to several terabytes of main memory capacity is not uncommon. But we also have applications that use completely unstructured data, so data of different granularities, where the accesses are going all the way across the memory space in arbitrary points in time. And on top of that, we have applications that use sparse data, so data that has so many holes that it's actually much more efficient to compress the data, remove the holes from the data, then in turn creating very irregular data access patterns. So that's a challenge, as you can imagine, for the memory subsystem. And on top of that, the entire compute system has changed. We've heard about vector extensions, and these only make it harder for the memory to deliver the aggregate bandwidth required. So if you double the number of your execution units, they can, in theory, sync twice the amount of data per cycle. So your memory has to somehow deliver twice the amount of data to actually efficiently utilize those units. On top of that, it's not just the CPU having bigger vector units creating more traffic, but we also have new units. Because scaling has stopped, we are looking towards accelerators, and I think in many sessions we've heard about neural network accelerators, matrix multiplication accelerators. We've seen in the industry other types of accelerators, GPUs being a very prominent example. And these accelerators, they're much more efficient than CPUs in many computation tasks. But guess what? A large fraction of their efficiency is derived from getting access to vast amounts of memory bandwidth and vast amounts of memory traffic. On top of that, if you add an accelerator into a system, you have to think about, well, how does the data move from the memory to the accelerator to the CPU, and maybe from there to yet another accelerator. So the memory subsystems really change from a memory on one side and the consumer on the other, namely the CPU, and a very unidirectional data flow, into something that actually has the data bounce around if you're not very careful in your system design. Again, increasing or decreasing system efficiency, if you will. So that's kind of the challenging outpost, that's the challenging landscape we're living in. And technology in many cases isn't making our lives easier. But for a change, in this presentation I actually want to highlight that technology isn't, I mean, you've heard about the lack of wire scaling, the lack of capacity scaling in DRAM and all of that, and the lack of process scaling. I don't want to bore you with any of the details of that. We've heard them a gazillion times already. Moore's law is kind of coming to an end. However, the technologists actually, I find it quite amazing, they come up with cool new things. So I've kind of 3 examples, and if your favorite gadget isn't here, I must apologize, but please talk to me afterwards. On the technology side, I think 3 things really can make a positive impact, can make our lives as the memory system designers easier. And the 3 things I've managed to pull out here is 3D integration here, which really gives us an opportunity for the first time to take different types of logic and memory and put them really close together. And that in turn reduces the wire length, it increases the number of pins we have available to connect memory and logic. So it has a huge impact on system design and on the design of the memory hierarchy. A little more specifically, inside the memory we can use that trick and create memories that have very high bandwidth, quite a huge number of pins that we can use, and can really help us with providing enough bandwidth to feed these wide vector units and the GPUs, for example, in the accelerator space. And finally, a technique that I'm excited of that you have seen in the news, I'm sure, and you've probably written research papers on, is non-volatile memory, which ideally, if it were the magic fairy dust, pixie dust, gives us many nice properties, namely it is persistent, it doesn't disappear when you unplug the power. It hopefully scales better than DRAM and kind of is almost as fast. Unfortunately, if you've seen some of the presentations today or you're aware of some of the research press, different technologies providing such a high-level interface have different shortcomings, and it isn't quite clear that all the things work together as they could, as well as they could. So there are technologies on the horizon that make our lives easier. It's not quite clear that there's none Pareto dominating the other in any way, which really means that we can do an interesting job, and that kind of brings us to what we are actually doing. So we are doing about 5 things, and they kind of relatively well map to the things I just described. So we're looking very closely at caches and interconnects. We are tracking and driving the memory roadmap, so we're looking at DDR5 at the moment, helping define that. We look at, well, if we can't move the data into the CPU efficiently, maybe the smarter thing is actually offloading the compute into the memory. I talked about non-volatile memories already. And we're looking at ways to think about, well, if we had a humongous memory that is accessed not just by the CPU, but various accelerators, can we think about really re-architecting the way we access that memory from the ground up to make it more efficient? So that's me and my research group. If you want to talk about any of these things, you want to actually make sense of the graph I showed earlier, please find me over a beer in a bit. Thank you.
Okay, and our next 2 speakers are from 2 groups which were set up at the beginning of this year. So the first is a group focusing on machine learning applications, Mattina. Gonna chase me around.
Okay, hi everybody. So thanks for the intro, Stuart. As Stuart mentioned, in January, we spun out from the emerging technology group, a machine learning research team that I'm leading. We're spread over 4 geographies right now, so we have a group in Cambridge. I'm based in Boston, as is Paul, who spoke earlier today. We also have several guys in Austin, Texas, and in San Jose, California. So we're We're a multinational organization working on machine learning. So I'm going to start actually in the middle with sort of the things that I wake up thinking about. And first and foremost is our model zoo, actually. So basically at the core of everything we do is characterizing and analyzing ML workloads and algorithms. This feeds basically everything else that's important. So what I mean here is by this model zoo is, we have a curated collection of models. So CNNs, RNNs, LSTMs, the whole alphabet soup of ML models. And when a new one is released, say, DeepMind publishes something about mobile nets, we basically get the Caffe or TensorFlow implementation of the model, and then we characterize it. And that characterization means running the model on our hardware, on existing, Cortex A or Cortex M, as the case may be, hardware, and sort of asking, well, where's the time spent? So it's kind of, brass tacks CPU architecture or architecture, but it's obviously important. We also run a bunch of scripts on each of these models that tell us about sparsity, which has been talked about several times today and is obviously important with NNs. It tells us about sparsity. It tells us about the data moving between layers. If you're thinking about running ML on a CPU or on an accelerator, you need to understand obviously the bandwidths and the data flows and how much data moves between layer 7 and 8 versus other layers in the network. And then the other thing this does is, the other output of the model zoo is, where time is spent, which lets us optimize software. It lets us take, the matrix multiplier, the GEM kernel, and tune it, because we know this is like the most important kernel for many NNs that we see coming out. And more interestingly, those same hotspots are the key targets for instruction set changes. So an example of this is, I think 3 weeks ago at Hot Chips, which, by the way, like 50% of the Hot Chips papers were NN or ML, which tells you kind of how hot and exciting this area is. But at Hot Chips, ARM talked about the new dynamic brand name and architecture. But at the essence of that, in terms of as it relates to machine learning, is new dot product instructions, which came out of this type of analysis that I'm talking about. So these dot product ops take a 32-bit lane in a neon unit, and they treat it as 4 by 8-bit, and they do 4 multiplies and a sum into 32 bits, which is exactly what you need if you're a neural network. So the ML model zoo, hopefully I've convinced you, is sort of foundational to what everything else that we do. I also listed on here highly constrained deployments. So we're looking at, M-class type of SoCs where you're extremely constrained in terms of power and memory footprint. So here, to touch on some of the talks earlier today, things like binary neural networks are something my group has looked at. Obviously, we look at accelerators. I won't linger on this as it's been covered well, but sparsity is something we look at. Data reuse and flow. One of the key things from this space was if you want to build a teraop per watt accelerator, you better not read an operand or 2 operands from a register file per cycle, because if you do, all your watt is going to be spent completely on the SRAM reads. Finally, at the far end, emerging algorithms, I worry about the next thing coming down the pipe from academia that could disrupt the ML market. We need to be ahead of that, be ready for it, so that we've got microarchitecture and architecture plans in place. Finally, the data center, both inference and training are in scope, and there are different aspects of this. So for training, we're looking at high precision, relatively speaking, so FP16, FP32, and even things like SerDes. If you care about training at scale, the interconnect between chips matters. Final slide. This is stolen from Paul's talk earlier today on the work that he did at Harvard. So we're hiring, especially in Boston and in Austin. So please see the ARM careers page and find me, and we'll talk. Thank you.
Okay, so one of the objectives we've been set by our new owners, SoftBank, is to spread happiness through the globe by delighting people with what computers and software can do. So on a good day, I might be delighted by some things that the computers in my sphere of operation provide me with. But if you don't get security right, you can have a very bad day. And Milosch is going to talk about that next.
Hello, welcome to this session. I want to speak about security at ARM. So I recently joined the newly founded security research group at ARM, which has been established early this year. And we have this unique position where we are able to coordinate different efforts across the company and make sure that the foundation for our decision is on a sound basis. So, for example, if you look at methods like, for example, separation and isolation, so that needs to be true from essentially the device level, obviously, which is like the most visible place where separation isolation is important. It's pretty common on server systems where you want to understand the impact of, let's say, a potential attacker to a system, and to simplify your security reasoning, you usually want to split a system into compartments and concentrate on a verification of the interfaces. So this is like a security best practice. This has been established with, I think, a good level of success on servers. But, for example, it's less established on, let's say, microcontroller systems. And from a developer perspective, you don't want to like reinvent new security architectures because just the fact that you run some code on a microcontroller, but you want to reuse like the security modeling, and you want to reuse, let's say, the mental model your developers established down to the most constrained microcontrollers, but on the other hand, also up to, let's say, your network level. So let's say if your device gets infected, you most likely won't have an update available for a certain time. So you need to ensure that you can continue using that device, but the device won't mess up your system. So I think these are like the interesting topics we need to solve. And you see that it would involve a lot of places in ARM. So because we're involved, for example, in wireless stacks, mesh networks, we can essentially influence all basically these levels to deliver on these promises. So I think, again, like a seemingly obvious topic like trust and identity, it's pretty clear. But, for example, provenance would imply, so let's say if I have an IoT system, I'm very interested on trusting my data, right? So I need to make sure that not only where my data is coming from, but let's say after I store that data and reuse it, let's say a year later, that there is basically an uninterrupted chain of trust where this data did come from, because I can influence decision by manipulating, for example, stored data. So trust and identity, I think, extends into basically these device interactions, and it becomes important when interacting with these devices and trusting their data. And trust has, of course, this additional aspect is if we can make transparent to the user what is happening with their data, and, for example, let's say what type of data is contained within their influence sphere and it does not leak into the cloud without need, we can increase like trust and acceptance effectively of these technologies. So side channels is, of course, I think, a very hot topic. So side channels, like again, the obvious aspects are on a cloud system, I want to run different people that don't trust each other on the same hardware. So how do I ensure that data doesn't leak in one or the other direction, that secrets stay basically within these boxes we establish mentally and practically with our system security? How do we ensure that we understand which information crosses these boundaries? And yeah, so like fixing, for example, the architecture side to ensure that we can contain, for example, side channels, for example, through while computing cryptographic operations or like by handling sensitive data. That would be another important topic. And increasingly, we of course face specification and correctness. So some software is simple enough that we can use mathematical approaches to verify its correctness, and this especially is interesting in the intersection between safety and security. So for example, if I have a security guarantee, how does it affect my safety delivery? So let's say if I successfully defend against a hacker attack, but break my safety promise and someone dies in the result, I did not really win that game. So some specific examples to make that less buzzwordy. So it's a lot about communicating, for example, and explaining how to use, for example, or what does end-to-end security mean, and how can I, like, for example, split out the notion of end-to-end security, for example, for data. And that all, the main theme behind that is to allow security at scale. So we want to trust that device policies are enforced by cryptographic means or hardware security. And in case you're interested collaborating with us, so these are the short-term projects that are coming up soon for us, or we are working already on them. And for example, memory authentication encryption is a very interesting topic for us. Side channel mitigations, and formal verification of system software. So if you are working on any of these topics, we really, really would like to talk to you. And we will have a Birds of Feather session on Friday at 2:15, where we'll discuss some of these topics. Sorry? Wednesday. Wednesday, yeah. So the last day of the conference. 2:15 right after lunch. So I'm looking forward to meet you guys. So if you want to talk about security, talk to me or to Hugo Vincent, who is probably in this audience here in the back. And yeah, so we're looking forward to talk to you. Thanks a lot.
Okay, 2 more speakers stand between you and refreshments. So without further ado, here's James to talk about, is it DCS?
DCS, yes, thank you.
Devices, Circuits, Systems.
Okay, so I have one slide because it's going to be immediately obvious to you how exciting this area is. I don't need to waffle on. Devices, circuits, and systems. So I need to first bust 2 myths. The first one is that ARM doesn't design chips. We do. My group does. We design them, we get them fabricated, we test them, we publish them. Yeah. Even as a soft IP company, you need to know people, or you need to be involved in hands-on design of real chips. Okay. That's important. The second one is that ARM doesn't care about circuits. You know, we just write RTL. Why do we care? Of course we care. You know, it's super important. If you want to get to 3 gigahertz, you need to have got your hands dirty. Yeah, you need to understand what the thermal issues are, what the power noise is like. You know, how bad the wires are in advanced CMOS nodes. Yeah, if you want to do 1 trillion devices, you need to understand how much lithium is in the world. Sorry to steal one of Rob's bullets from later. You know, energy delivery to these things is really important. How low can you get the power on these things? Yeah, that's not a pure RTL hands-off approach. Yeah, so ARM does all of this stuff. So to speak to some of the specifics then, you know, it's a very broad area, but some of the specific things we're doing. So low power IoT sensor nodes. So our new owner is very passionate about getting to 1 trillion. They're not all going to be 1 watt devices that will consume all of the power the world generates. So how low can they go? You know, so we are building, designing and building sort of 10 microwatt level MCUs. Okay. Third myth here: ARM is a digital company. To do those super low power things, you need to understand the sensors. That's an analog interface. You need to understand the power delivery. You know, if you're running a 300 millivolt sub-threshold, very efficient digital system, that doesn't come for free. You know, your battery is 1.5 volts, 3 volts, whatever. So to convert that voltage into something you can use, that's important, right? And that's part of the story. You can't cheat. You can't just say, look at my, you know, super efficient digital and then magic up a new battery. So speaking of batteries, can we go batteryless? Can you go to energy harvesting? Yeah. If you've got 1 trillion devices, super hard to go around and change all the batteries in them all, super destructive to just stick them all in landfill. So energy harvesting is really important, okay? And again, we're not manufacturing energy harvesting devices. I'm not that interested in different kinds of solar cell other than how to use them, how to make the most out of them, how to put system hooks in such that you can adapt to lower power that you get at twilight with solar cells. You know, we've demonstrated some work that has an adaptive system to enable 40% extra compute capability out of a solar cell scenario. Not something you might expect to see on a research agenda, but low power standards. So all of this stuff has to be deployable, right? Okay, so I say we build chips, but we also need to enable other people to build chips, yeah? That's where all of our hardware money comes from. So standards are really important. Making things deployable, making advanced power-saving technologies describable, verifiable, and you know, those things flow into EDA as well as in the IP, the description of the IP itself, and the design of the IP. To leap then onto, so I covered low power, very low cost, yeah? Printed electronics, the vision here is to enable 1 cent disposable microcontrollers that will be on every tomato, lettuce, Band-Aid, whatever in the whole world. To do that, there are a number of things that are, orange lights already? A number of things that are constrained today. In printed electronics, it's the, in particular, it will be the design cost. You can't just take a low-cost manufacturing process and say, okay, yeah, you know what, spend a few $1 million on designing this 1 cent chip. So that's something that my team is focused on. And then on the performance end of the world, Moore's law has been widely reported to be on life support. The post-5 nanometer question is on when and how we pull the plug. And then, of course, that leads into emerging process technologies. What comes next? You know, and how do we live with those things? Is it plasmonics, spintronics? Are there going to be graphene wires that take all the pain out of interconnect? How does the system look? How does the CPU look? All kinds of interesting exotic technologies that we're looking at there, some of which I can't even name. But yeah, so that's my area. This is my face. I'm around all week, so if you're interested in any of these things, come and talk to me. Thank you.
Thanks, James. I was really pleased to see all the research thrust leads there starting to point to their faces. So I'm back again. The reason I'm back, we have one more talk, but this is a little bit of a, I know you've been sat here for a long time, but I really want you to listen to the last one and take away some messages. The reason is we've talked about the new things. So you've seen the new logo. ARM's changed. It's changed because we have, it's not changed. It's changed anyway. It's changed because we've obviously been acquired by SoftBank, and that has changed the investment and the focus areas that we're moving forwards in. So a lot of what you've heard today, although it also applies to this wonderful world of Internet of Things and distributed devices, it's still talking largely about how do you design devices and the chips that go in devices, and how do you program them to build things. What's really important for us now moving forwards as well is the area of research into that distributed system. So a lot of our historic collaborations were all about optimizing for HPC, optimizing machine learning to go in an edge device. We're also now very interested in collaborating in areas that read on the broader distributed systems. And Rob, who's going to come up now, is going to talk about our areas and our agenda in that space. So please listen to this, because you might want to go back and talk to people in your computer science departments, or maybe in your legal and ethics departments, about how they might collaborate with ARM.
All right, so I was thinking, what's worse than being last and being between people and beer? And I've concluded that much worse than that is actually being last and having told everyone that I should be listened to. Right, so anyway, that's frightening. Nonetheless, here we are. As John mentioned, these are the sorts of things that we're looking at as new initiatives in ARM research. We recognize that these areas are in and of themselves complicated enough and important enough that the idea that ARM research as a group of 100-ish people could be a significant fraction of the world's research in that area is nonsensical. So it's all about collaboration, and that's what we're really interested in pursuing. What are the sorts of things that we're looking at? Well, there's the distributed systems, as John mentioned. There's also optimization of these systems in a world of constraints. So power, latency, bandwidth are all key. It's important if we're going to get to this vision of 1 trillion things that the solutions be scalable. So I made this object, or I put 1,000 of these objects together. That's all very interesting. How do those scale up by multiple orders of magnitude? Milosch mentioned end-to-end security. That's important. And this last area of data-oriented services is an interesting one. Sort of an analogous view in mobile systems is ARM provides a lot of technology behind mobile compute, but ARM doesn't do apps development. We don't know anything really about apps development. We don't expect to be the apps developers. Similarly, in a world of 1 trillion things, we don't expect to develop those apps either, but we would like to be involved in producing the infrastructure that works there. Okay, so since you all waited this long and you've been here all day, I thought we should at least do something that's mildly amusing. So one of the questions is, if we're going to do 1 trillion things, are there in fact 1 trillion things at all? How would you go about connecting them? At the moment, there are around 400 billion beverage cans produced every year. So if we instrumented all of those using James' magic plastic device, that gets us 40% of the way to 1 trillion right there. So sure, there are 1 trillion things. There's still 100 billion sheets of paper, despite the paperless office having come into existence 20 years ago. What if we spread 1 trillion things uniformly across the surface of the Earth? Well, that would be 2,000 things per square kilometer, or we would each have 140 of them if we spread them uniformly across human beings and so on. So 1 trillion things can definitely exist with certain assumptions. So then the next question was, well, what else? What other sorts of things are there? Well, let's see. Could you have 1 trillion batteries? Well, if you look at a lithium cell, for example, it contains about 109 milligrams of lithium in a coin cell. So 1 trillion of them contains 109,000 tons. That seems like a lot of lithium, doesn't it? If you've seen lithium react with water, that could be interesting. Nonetheless, how much do people make? Well, right now they make about 32,000 tons a year. That's where, there's plenty of reserves of it out there. But a lot of that is going into Teslas. So the idea that it all goes into coin cells and that those go into things, this leads us to the conclusion that perhaps energy harvesting is a good idea. And so this is the sort of thing that we've been looking at, and just, well, what other limiters are there? And there's plenty of them, but one of the intriguing ones is how many designs are there? So if you take, how many of you teach RF design? Right. Now, if you add up the total number of people worldwide who do RF design, it's sort of about 5,000. And if you actually find an RF designer, you will find that the number of people who do RF designers is 1. That person that you're talking to does RF design correctly. There are a few other people that person knows who do it almost correctly. And then you extrapolate from there. But nonetheless, there really aren't that many people out there who do this stuff. So if you divide 1 trillion by 5,000, then you get 200 million things must be covered by each of the world's 5,000 designers. So that leads to an interesting design problem, doesn't it? So there's kind of a bottleneck there. Similarly, there's a bottleneck on IC design teams of 20,000-ish. How about people who can write software? Well, there's sort of 20 million of those, maybe. So now we're getting into an interesting realm, because now it looks like if you're going to have, you kind of wind up in trillion thing space with 2 different paradigms. One is that you have a very small number of designs that are used in a wide, huge variety of applications. Another is that instead of that, you have a huge number of designs, but they're all designed by software engineers. So, both of these are interesting. So what does that mean? Well, we don't know, but it basically means that there's a challenge going forward. This slide always comes up really slowly, so it's likely to disappear from sight soon. Nonetheless, where do these trillions exist? They exist in this sort of space of edge to cloud. The trillions are really over in the things side. But then these things communicate with the rest of the world. They produce all kinds of limiters, as I mentioned, on bandwidth and so on. And we need to think about those as well. So the systems aspect, the interconnectedness aspect are important. And the software aspects of these, the connectivity aspects, all of this is important, the security. So I tried to summarize this into sort of 4-ish bullet points. And again, this is the last slide, I believe, between us and beer. No, there's a whole realm of more of them up here. All right, so I don't have any more that I don't. So after this, you can stop listening. If you're going to have a trillion things, if the things by themselves are not producing some value, so if there's not some value in putting a plastic circuit on a tomato or a tomato, there's no real need to do it. But once you've got them, the things by themselves, they need to work together. And that's where the integration, the systems aspects become very important. The communications aspect become important. We also have, they have to work automatically because you're not going to get to scale if there's humans involved. And they need to work resiliently, where resiliently includes the security aspects, it includes the reliability, and it includes all these things. So there's no shortage of research tasks for you to be working on and come back to the summit next year and tell us all about the progress that you've made. And similarly, if you want to talk about collaborations in this space and you've failed to memorize anybody or anything, then go talk to John. All of you. Or find me, or find Gary Carpenter. Is Gary here? No, he's cleverly escaped. But nonetheless, we'll point you to him. And we're all very interested in talking about this and in establishing these collaborations, because that's really, I think, the key for ARM working in this system. It's why we have this summit. It's how do we get all of you together with us doing things that will enable the next trillion devices. I'm on my yellow light, so I'm done. Who's up next?
I'm going to ask all the ARM speakers. Come on. Stage. Guys, come on stage. To stage. All the ARM speakers.
He's going to point us all out.
Hang on. It's going backwards, sorry.
Now you've done.
It's broken.
You broke it.
I broke it. Right. So rather than just putting a slide up at the end with who the people are, everybody you've just heard talk to you is on the stage. Thank you for your patience through that session. I know it was long. I know it was the last thing in the day. Hopefully you found something to latch onto, something that you'll be able to follow up with any of these guys on here. Or remember, failing that, talk first to Chris, or talk to me. We'll all be around all evening over dinner and later in networking and around in and around the bar area. So thank you. The other last thing I wanted to say is, you've got one of these. You'll have heard our ambitious agenda and our ambitious thinking here, and you've heard Rob talk about the new area. One other change that's coming is we're investing a lot more into these areas, and that means we are recruiting a lot. So if you have any students or you're interested, point them in these guys' ways, because they're all hiring. And Rob, and Gary, who works with Rob on the Internet Services agenda, is especially hiring. We aim to grow our research group by another 50% over the next 12 months, just to give you a size of our ambition. So we currently stand at roughly 110 individual contributors. We aim to add 40 or 50 more over the next 12 months. So once again, thank you for your patience. I'd like to thank all the guys who put the efforts into talking to you together. Thanks guys, and thanks from me.